Okay, so let's summarize the story so far, right? We have come up with how we can build a CPU, a central processing unit, that's capable of performing certain kinds of operations or computations, okay? The sequence of operations that needs to be performed, the exact set of steps, is typically stored in memory, and at some level that can be thought of as the program, the instructions that are actually telling the computer what to do, right? The operations obviously need to operate, right, or perform their work on some data, right? Where does that data go? We assume that that data is also stored in memory, right? And because of the speed related issues, right, we find that we might need to sort of be explicit about getting data from the memory into the CPU and taking the data back from the CPU to the main memory, right? So there is this concept of moving data. And where computers really excel is that, you know, everything that I have described over here is very automatable, right? It's very sort of straightforward, repetitive work, and we are able to build electronic circuits that can do all of this very fast, right? Like I said, when I say very fast, I literally mean several orders of magnitude faster than what a human brain can work at, right? But that's it. I mean, the kind of operations it's doing, of course, are very simple, right? So clearly, in order to appear useful, it's able to fool us into thinking that it's doing something useful by doing whatever it is being told to do extremely fast, right? It's not coming up with instructions on its own, it's not building the data on its own, it is doing exactly what it's been asked to do, but it's doing it so fast that it actually becomes useful for us. The natural question that would come up is, okay, so far I have the ability to perform additions, multiplications and so on, but what if I want to do the same kind of operation many times on slightly different data, right? A simple way of looking at that might be, let's say that, you know, I'm trying to even do something like just predict the average temperature of a day, right? I might want to do something whereby I have some numbers corresponding to the temperature that's been recorded in each day, and I want to do some kind of averaging of that, right? And say, okay, you know, this was the average temperature on this day, this was the average temperature on the next day, this was the average temperature on the third day, and so on. And based on that, maybe come and see, okay, can I predict what it's going to be on day 4 or day 5 or day 27, okay? As you can imagine, what is ending up happening over here is I have some kind of highly repetitive set of tasks that is happening, right? The averaging is being performed on all the numbers corresponding to day 1. And if I look at day 2, I have two ways of doing it. Either I could write down the same set of operations for day 2 which I did for day 1, but now pointing at different memory locations corresponding to the data for day 2. Or I could look for a shortcut and say, hey, you know, can I take some set of operations that I have defined for day 1 and just repeat this for day 2, okay? So this idea of a repetitive task, something that needs to be performed substantially the same kind of work, possibly on a different or new set of data, right? Most likely on a new set of data, because just, you know, repeating the same operations on the same data is not going to give us different results. But the same set of operations on different data is something that could be very useful, okay? Now, how do we do it? Like I said, either you just keep on repeating the instructions as many times as you need, or figure out how to repeat a set of instructions, okay? That's where the concept of a loop comes in, right? So a program is a sequence of operations. What I have is, you know, there is step 1, then there is step 2, step 3 and so on up to step n, right? So there are some set of operations that have been defined as part of a program, okay? The CPU keeps track of which is the next instruction to be performed. So typically there would be one sort of, you know, physical piece of hardware inside that CPU, which we usually call the program counter, right? The program counter's job is to basically say, hey, you know, I'm going to keep track of where you are. Right now, you are looking at step 1, okay. And once you finish step 1, the program counter increments and says, okay, now go to step 2 and perform this work, right. After it goes to step 3 and so on, okay. So the program counter is just going to increment 1, 2, 3 and so on. As it increments, it pulls out operations, step 1, step 2, step 3, step n. Each of these is most likely some kind of an ALU operation. Could be multiplications, additions, there might even be some loads and stores involved, right, because after all I need to pull in data from somewhere and decide what to do with it, okay. So all these steps could be either ALU operations or memory operations, loads and stores. So the bottom line is I am now able to perform this sequence of n operations. What if I want to repeat all of this some k number of times, where k is again something that's some kind of a variable, right. I don't quite know ahead of time how many times I want to repeat it, right. If I knew that I wanted to repeat step 1 to step n twice, maybe the simple thing to do is just copy all of this down here and say, okay, just repeat it. If I knew I wanted to do it 5 times, okay, maybe I could copy it 5 times. If I wanted to do it 50 times, it starts to get a little problematic, right. I mean, now my code is becoming too big, okay. But what if I want to do it an unknown number of times, where the number of times will only be known when I have actually done some work, right? Then I can't even think of making all these copies. It's simply not possible. So what I do instead is I bring in a new piece of information, right, which I call my loop counter, right. And the loop counter, what I do is every time that I have gone through this loop or this sequence once, I increment, add 1 to the loop counter, and I compare it with k to check whether I am done or I need to continue, okay. Now think about it, a loop counter essentially looks like a value which starts out at 0 or 1, we will get to exactly why 0 or 1 and how things are implemented in programming languages later. But right now let us assume that it starts at 1, okay. Each time I finish one sequence of instructions, I increment it, right. So then the loop counter becomes 2, and then it becomes 3, finally it becomes k. And when it becomes equal to k, I say, okay, now I am done, I don't need to repeat this, okay. What should I do? I basically get out and start performing operations which are after this step n out here, okay. So this loop counter by itself, if I think about it, what do I need to do? I need to be able to take a value, I need to add 1 to it, and I need to compare it with another value, okay. It seems reasonable enough that I don't need custom hardware for this. I can just use any value that is stored in memory or a register of the computer in order to sort of take the job of this loop counter, right. So I don't really need anything new for this, it's just either a register or memory, right, and I don't really need to sort of bring in anything new. I already know how to add 1, that's one of the ALU instructions, and I know how to compare, yet another ALU instruction, right. But what I need to do when the loop counter becomes equal to k is something new. What is that? I need to take the program counter, which would normally just have gone tick, 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 tick successive values, and say, hey, instead go point at step 1. So change the value of the program counter completely, right. Instead of going to +1, go somewhere else, right. This is a new type of instruction, something that we have not encountered so far. We had ALU instructions, we had loads, and we had stores, where loads and stores can be combined together as memory type instructions. What we have over here is something new, okay. Effectively, this is something that we call a branching instruction, right. So what we are saying is we can also generalize, we don't need to only perform loops, we don't need to restrict the changes in the program counter to always just go back a fixed amount. In general, if I say, hey, you are allowed to put any value that you want into the program counter, it means that you can now jump or branch to any memory location essentially and start looking at the values over there and execute them as code, okay. So any condition could be a trigger. It might even just be that I have a particular operation or a particular instruction in my memory that says jump, right? Don't ask any questions, just jump. What does that mean? Take the program counter, put a new value into it. Okay, don't add 1 to the program counter, just jump somewhere else. Okay, and what is done over here is that this is affecting what is called the control flow of the program. Okay, because if you think about it, everything that we have talked about so far, the ALU is doing something called data processing, right? The loads and stores are also data processing. They are getting data from the memory into the registers or from the registers back into memory. The branches, right? The loops, conditional branches, unconditional branches, these are essentially affecting what is called the control. It is telling you how to change the behavior of the program. It allows you to now start executing a new set of instructions, or depending on what happened so far, I can even make a new choice and go somewhere else and start doing something new. So this is called changing the control flow of the program. Okay. So overall, right, once again what we can do is just recap what a CPU is capable of. And what we find is there are fundamentally 3 types of instructions, right? There are the operations, arithmetic and logic. And since we found that we did not have the ability to build incredibly large but still incredibly fast types of memory, we split the memory architecture so that our memory that is used to store the data versus the memory that's used for temporary holding storage are different, which means that we now need to have a new set of instructions that handle loads and stores, right, getting data from that external memory into the registers and back. And then what we said was, hey, there is also some kind of control flow that will allow me to repeat instructions, repeat a sequence of instructions, or just look at where I am right now and go somewhere else and do a different set of instructions. So those control flow altering operations are the branches and the loops, looping instructions. Interestingly enough, just these 3 classes of instructions are pretty much all that you need in order to build up a complete working computer, right? In principle, you could probably even get away with something less than this. You might be able to emulate some of the other operations using parts of these, some of these operations in order to emulate some of the other kinds of operations. So it's not that this is fundamentally the bare minimum requirement, but this is a logically easy to understand, right, subset of instructions that are required. Now in practice, what you will find is that CPUs typically have a lot more instructions of various other kinds. That's primarily more for performance reasons, right? It turns out that by adding other kinds of instructions, you can sort of improve the performance for specific kinds of operations. But if you go look at the core of what a CPU actually looks like, these are the 3 main types of instructions that you are going to find. And these are sufficient for whatever useful purposes that we want to build out of it.